Hello, everyone. Welcome to another AI research seminar. Today we have a distinguished speaker, Ravi Ramamoorthi. He's going to be talking to us about his work on neural radiance fields for view synthesis and beyond. So I'm going to give it to Ravi now.
All right, so thank you very much, Kevin, and thank you for inviting me. I'm going to talk about our work, which aims to reproduce these virtual experiences of real-world scenes. Here, you want to be able to take a few images of an object of interest. The images look something like this. Thereafter, you want to be able to have an output realistic virtual experience. Notice the reflections on the puddle, the reflections on the bike. And all of these realistic effects are captured as you're able to freely move your viewpoint around. This gives you the potential to experience these images in a virtual or augmented reality setting, or to promote 2D photography to fully immersive 3D experiences. This idea can be seen in the context of something known as light fields. The concept actually has a very long history in the physics literature, going back to Gershon and Moon's idea of a light field and even earlier. The key quantity is the intensity of the light or the radiance in the scene, which is a function of the spatial position x, y, z, and the direction you're looking at it, theta and phi. As such, it's a function of 5 parameters, and it's a 5D representation. If you know the radiance or the light flowing through any spatial location, any direction, then you can create images from any viewpoint because you simply index into the radiance of the light field. In free space, in the absence of occluders, the seminal work from Leboy and Hanrahan, and later also Gottler et al. Simultaneously with the Lumigraph paper, showed that this 5D light field can be reduced to 4D, essentially because the intensity of light or the radiance remains the same along straight lines, and therefore you can remove one parameter, which means that if you have a 4D light field representation, you can capture any images in the exterior of the convex hull of the object or the interior of an environment. In fact, images can be viewed as 2D slices of this 4D light field, where you're simply inserting acquired images, and the goal is to reconstruct this light field. Here is a simple visualization. Since I can't draw things out in 4D, I've just shown it in simple flatland where the light field is 2D. Assume you have a number of cameras around an object of interest where you're taking images. Obviously, it's possible to simply interpolate the camera views, but you can do better. If I want to zoom into the object, I can put a new virtual camera as shown here. And in order to create the images from there, I actually take a ray and I project it back to where the source cameras are. In this way, I can combine and resample rays from multiple cameras to support zooming in, and in fact be able to construct any kind of image in the outside the convex hull of the object. This is a problem known as novel view synthesis, where your inputs are sampled images of the scene, and thereafter you want to be able to render these novel views. As shown in the visualization on the left, you have a number of images, and thereafter you want to be able to do the thing on the right to be able to create images from novel viewpoints. Of course, to go from the left to the right, you have some kind of representation of the scene. And much of this talk is about the history and challenge of finding that correct representation of the 3D scene. Until the mid-2010s, essentially these representations were classical 3D geometry. You reconstruct some notion of the 3D geometry of the scene, which is either explicit 3D geometry or some kind of a disparity map that says as you move, how much the points shift. And based on that, you can do these renderings, which look pretty good, but of course have certain effects of blurring, etc. for, I would say, about 20 to 25 years since the original light field papers, which actually postulated you didn't need a representation of the 3D scene, you could just interpolate the original images, but then the sampling rates become too high. So for practical applications, you still need to resample and create an implicit representation of the scene. This is generally how we view 3D geometry, and so these representations and these methods progressed for 20 to 25 years. And got fairly good, but still there is a certain level of realism you can't get beyond. In the mid-2010s, with the advent of AI and deep learning algorithms, techniques were developed that could employ now the power of modern machine and deep learning. Notably, work I did with my former postdoc, Nima Kalantari, in 2016. And now the quality improved, but we were still dependent on this notion of implicit geometry or disparity. Towards the end of the 2010s, there were representations such as multiplane images, which is essentially a sampled volumetric representation. You have a number of planes on which the geometry is represented, essentially as a color and a transparency. And this, again, led to an improvement in the quality of images. The slide is from the PhD thesis of my student, Pratul Srinivasan, which was recognized with an honorable mention for the ACM Dissertation Award, and shows our journey over his thesis in discovering the right kind of representation to be used. We started with trying to predict the light field generally, then use sampled volumetric representations like multiplane images. And finally, I will talk about the widely popular neural radiance field method, which is a continuous volumetric representation. So first, I want to give some background on light field cameras, which was one of the initial kind of motivations for our work. Around about the early 2010s, Renning and others developed these kinds of consumer light field cameras where you could essentially, for a narrow range around the aperture of your main lens, by using technologies like microlens arrays, you could capture the entire 4D light field. And that enabled photographic applications like you could change your viewpoint after capture, again, within a narrow range. And most interestingly, that you can refocus the image after capture simply by reparametrizing the light field. Now, the way these light field cameras are set up, you can think of them as essentially being a 2D array of cameras, as you would need in order to acquire the light field. If you have a 2D array of cameras, each of which is capturing a 2D image, then you can acquire the 4D light field and you can perform view synthesis. However, in order to enable this 4D light field representation in a 2D imager in a light field camera, you need to make some trade-offs. In particular, for this high angular resolution, this is from the Lytro Lume camera, which was introduced about 2018, you have an 8x8 grid of sub-cameras, which can essentially be seen as sub-apertures on your main lens. And if you're doing this, you are effectively getting those additional cameras and that additional resolution from the resolution on your main image. So if your main image is 10 megapixels, the resolution will be divided by a factor of 64, 8 times 8. And therefore, your spatial resolution actually goes down a lot, which is one of the reasons why light field cameras never really became hugely popular, because you're giving up a lot of spatial resolution to get this angular resolution. Now, one solution around it to not give up the spatial resolution is the notion of angular super resolution. If you had these sparse input views, in this case, just the 4 corner images, now this is effectively the setup you have on a modern cell phone, where typically instead of having a single camera, you actually have 2 or 3 cameras with different lenses, and then you actually do some computational photography to combine the images to get a nicer looking picture. This is what it looks like. Although the baseline is small, you notice that there are occlusions. The leaves and flowers are occluding the person. And it is a non-trivial aspect to go from these images to actually produce a smooth view interpolation. Our goal is to synthesize the novel views, effectively synthesize the remaining cameras so you can use a much sparser camera array or light field setup. I was also on the technical advisory board of this company, Pelican Imaging, which is trying to build camera arrays for mobile devices. If you do this, there's no loss in image resolution, and you can synthesize the intermediate views to get your full angular benefit as well. So here is our result. And you can see that we now have a smooth motion. You're able to smoothly vary the image, capturing all of the occlusions and other effects. And this was an important result because of the quality of imagery you're able to get. We're using just these 4-corner camera views, showing also the power of deep learning algorithms, coupled with conventional geometry representations, a representation of disparity at the time. Now, if you can do this from the 4-corner images, then how about being able to do it from a single image? In work we did several years ago with my student Prathul Srinivasan, we effectively, from a single image, tried to just predict the light field directly, as if it were captured from one of these light field cameras, and predict both the light field and the depth information from a single image. Of course, we had to limit it at the time to specific classes, such as flowers in this case. We were able to get fairly accurate depth representations, and in fact, multi-view depth, where you see these kinds of parallax effects, which then allows you to do narrow baseline view synthesis from only a single input image. The power of this representation is that you can take your legacy 2D photographs, such as you may have captured with a regular camera or a cell phone camera, and promote them to these immersive 3D experiences or 4D light fields. Of course, in that case, we were limited to a particular class of images of essentially flowers and plants. But subsequent developments in this field have now progressed very rapidly so that we are actually able to get pretty high quality results from only a single input image. However, those results were all limited in this light field camera setting where you have a relatively narrow baseline of how much your views can change and how far you can change the viewpoint for view synthesis applications. So what happens if you want to have much larger changes in viewpoint, much larger baselines? In this work on stereo magnification about 5 years ago, Zhu and Novasavli and colleagues showed that if you had a persistent representation, not simply predicting the light field generally, but you had this representation which they call the multiplane image or MPI. The concept goes back to the early days of light fields and view synthesis, which is from Zaleski and Golland in 1999. The idea is to represent the scene as a number of planes or layers at fixed depths, where each layer is a conventional color image, RGB image, but also has an alpha or an A channel for transparency. And therefore, you can composite all of these layers to get a representation of the scene. This can also be seen as effectively a volumetric representation, but discretely sampled on discrete depth planes. Then you simply render this representation from a novel viewpoint. You can think about ray tracing it or projecting it onto the novel viewpoint. and you can get a fairly wide baseline recreation of the scene or enable you to do view synthesis. We were interested in this idea, and the question is, how can you do really high quality, wide baseline view synthesis? We introduced this notion of casual capture, where you're effectively taking a 5x5 grid of images, but they don't have to be exactly on the grid. They can be somewhat off. They're just taken casually with a cell phone. Once you've done this, you promote each view to a local light field by predicting the multiplane image given that view and its neighboring views. This enables you to effectively synthesize the local view light field around this viewpoint quite easily. And then what you end up doing is you blend the nearby local light fields to get an even better representation that is higher quality. Going back to the example I showed in my first slide, where you can see also these reflections on the puddle and on the bike. Therefore, it's not just capturing the kind of view-independent diffuse or Lambertian effect from a matte surface, but it is also capturing these glossy effects, these reflections. A lot of very high-quality visual effects are being captured for these immersive experiences. In fact, you can also analyze theoretically how many images you would need. For that purpose, we go back to the seminal work on light field reconstruction from Chai et al. In 2000, where they showed that in terms of signal processing in the frequency domain, the Fourier spectrum of the light field, which is bounded by a certain minimum and maximum depth, is given by these wedges in the frequency domain. Okay? And effectively, the slopes of these lines are determined by the minimum and maximum depths. Here I've shown the standard classical result of if you sample from multiple viewpoints, then effectively what you get is these replicas of the central spectrum, which is what you want. The central spectrum is what you want, but sampling induces replicas. That's a standard result in sampling theory. In order to remove these replicas and get back the central spectrum, you need to apply a reconstruction filter, which in this case tightly bounds the central spectrum and excludes all of the replicas from sampling. The interesting point is that this reconstruction filter is this tight parallelogram that captures the effects of this double wedge. And it can be thought of intuitively as reprojecting the light field to essentially the median depth. It's not actually the median depth, it's the harmonic mean of the initial and final depth, so of the two slopes. But essentially, it's just reprojecting. And in terms of an intuitive analysis, the cameras can be as far apart so that that reprojection does not induce an error of more than 1 pixel when you reproject. So all of these results were derived a long time back by Chai et al. What we were able to show is that the machine learning pipeline to predict these multiplane images and then interpolate them gets surprisingly close to the theoretical bound. In particular, if you have a maximum disparity of 8 pixels, that means your adjacent cameras, the difference between the depth at which you're projecting and the depth it actually is, if that difference can be brought to under a pixel, you're good. But what do I mean by disparity of 8 pixels? You divide the scene into 8 planes. And therefore, you're effectively localizing the depth of any point into one of these planes, which is used for reprojection. Within that plane, the disparity will be less than 1 pixel. So effectively, you're able to handle a disparity of 8 pixels by using 8 planes in your multiplane image. Similarly, with 16, disparity of 16 planes, 32, 64. At 128, you start breaking this theoretical bound. The reason for that is now the disparity is 128 pixels, so adjacent images don't see enough of the same scene. so that the estimation of the multiplane image starts having errors in it. But at least up to a disparity of 64 pixels, by predicting the multiplane image with 64 planes or layers, we can actually get the theoretical bounds. What that means is also that you can break the Nyquist limit by a factor of 64 in each dimension. If you had no notion of a 3D representation, your cameras would have to be finely spaced so that the maximum disparity between adjacent images is 1 pixel. We now allow disparity of up to 64 pixels, and therefore we can reduce the sampling rate by a factor of 64 in each dimension. So the number of samples or the number of cameras can be reduced by a factor of 4,000, which allows us to reproduce these kinds of very high quality visual results with 25 to 50 camera views. So we introduced our method local light field fusion. Here are some examples of scenes we were able to capture with it, including people, including objects that have a lot of reflections, such as the cars, including some very complex occlusions and foliage. And we are able to give precise bounds in terms of the number of images you need to reproduce these high quality results. So all of that was now the second column in this slide. These are sampled volumetric representations. The final step we made about 3 years ago was to go beyond that and introduce a continuous volumetric representation that is not discretized into these multiple planes. And that is the idea of neural radiance fields, where you use a neural network known as a multi-layer perceptron to essentially predict the volumetric properties at any point in the volume, and now you have a continuous volumetric representation. So I'm going to play the video for the original work on neural radiance fields, then talk about the method in somewhat more detail and some of the impact that it's had. This video has audio. Please let me know if you don't hear the audio.
We present neural radiance fields, or NERF, a new method for representing complex scenes that achieves state-of-the-art results for view synthesis. Given a set of input images of a scene, which in this visualization is a Lego bulldozer, we optimize a volumetric representation as a continuous function which is defined for any 5D coordinate, consisting of a location and view direction. We parameterize the scene representation as a fully connected deep network that takes in a single 5D coordinate and outputs the corresponding volume density and view-dependent emitted RGB radiance at that location. We then use techniques from traditional volume rendering to composite these values along the camera array to render that pixel's color. Since the rendering process is fully differentiable, we are able to optimize the scene representation by minimizing the error of rendering all camera arrays from a collection of standard RGB images. Our method is able to reconstruct high-quality novel views from a sparse set of input images of a scene. Our strategy outperforms prior work that also represents a scene within the weights of an MLP, as well as prior work that represents a scene as a set of multiplane images or as a discrete voxel grid. Here, we visualize additional results across a wide variety of real-world scenes, each captured with 20 to 80 input images. Our neural radiance fields are able to render photorealistic novel views of scenes with fine geometric details and realistic view-dependent effects. We're able to capture all of this visual complexity in just the weights of a simple, fully connected network, requiring only 5 megabytes of storage for each scene. We can visualize the detailed view-dependent effects captured by our representation, such as the sharp reflections and specularities on this car, and the glossiness of this room's television and conference table. Our representation captures high-quality scene geometry, such as the details on this red flower, and complex occlusion effects in these tree leaves and ornaments.
All right, so going over some of the details more. The views are generated with traditional volume rendering. This is one of the major departures from the traditional representations used for view synthesis, which use the classical representations of 3D geometry. Here, there is no explicit 3D geometry. It's actually a volume. And that is an important deviation from the traditional approaches. The traditional approaches of recovering geometry kind of always failed because if the geometry was inaccurate, because of algorithmic problems, because of camera calibration, then once you made a mistake, the visibility is messed up and it's very hard to recover. On the other hand, using a volume enables you to keep everything smooth, makes it completely differentiable, and makes it easy to recover the shape. So you generate views with traditional volume rendering where you march along the volume. And now you use an MLP for each point in the volume. It tells you effectively what is the density or the occupancy or the opacity in the volume. Technically, I mean, it is the extinction coefficient of the volume, as well as what is the color. Effectively, you're viewing this as an emissive volume. So what is the color coming from that point in the volume? Thereafter, you can just compare the resulting image to the images you've captured, and you can make sure it fits the captured images. You simply need to minimize an L2 error. You can do fancier things, but essentially just minimize the RMS error between these images and do gradient descent on it. All of the steps are differentiable to determine what the parameters of the MLP are. Now, volume rendering has a long history in computer graphics, and you get these beautiful effects such as absorption, scattering, emission of light. There's actually no scattering here in our model. It is not intended to be physically based. It is just doing the standard volume rendering where light can be absorbed in the medium. That's what the volume density of the medium corresponds to. And we have this notion that light is being emitted from the volume. Note that this is, again, not a physical representation. It's a representation of an emissive volume. So the lighting in the scene is actually baked in because you're just trying to do view synthesis. What does it involve mathematically? You're tracing a ray from an origin O in a particular direction. This is standard ray formula, O plus TD. The color composites along all of the points on the ray. So you have these weights Ti, which is essentially how much the ray is attenuated or how much light is blocked earlier in the ray, and times the opacity of that point. So if it is an opaque point, obviously you'll get the full contribution from it. Otherwise, you'll get a lower contribution, and times the color. How much light is blocked earlier in the ray is essentially 1 minus the probability that the ray is absorbed. And that's essentially what this alpha is. Again, it is a notion of opacity. So if the points before that are opaque, then the contribution is completely blocked. Otherwise, it's partially blocked. And then how do you compute alpha? That, again, depends on the density in the volume. And essentially, this is a way to numerically integrate along a segment. If you look at the first order Taylor expansion, it's simply sigma I times delta I, which is the volume density times the extent in which you're moving in the medium. So this is all very standard volume rendering equations, just considering absorption and emission. You could do all of this, and it has previously been done in work like neural volumes, which is a seminal early work, with a discrete volumetric grid that stores RGB sigma. In effect, that's also close to what a multiplane image is. But our insight is to use a continuous volumetric representation where instead of the discrete grid, you just plug in inputs x, y, z, theta, phi, you go through a multi-layer perceptron, and then you get the color and the volume density. Of course, this requires some further refinements. So first, we can consider a toy problem of storing 2D image data. Usually, we store an image as a 2D grid of RGB color values, but you could instead give X and Y as input to the multi-layer perceptron and let it predict the color RGB. That's a simpler version of our volumetric representation. Now, if you try to do this, actually, it fails. You have a ground truth image. You're just trying to memorize the single image. There's no generalization. There's no real claim to intelligence. We are using methods of deep learning and artificial intelligence, but we're just specializing it and memorizing a single image We're not making any claim to actually be intelligent. And it fails even so. So we had to come up with this method known as positional encoding, where effectively you take the point and you give the MLP a higher dimensional vector of essentially a Fourier series of sines and cosines, but with the periods or with the frequency of the Fourier series going up in powers of 2. So it has a lot of information to work with higher frequency information. We do analyze this in a companion paper from NeurIPS 20, and this general method of positionally encoded neural implicit functions have found wide impact well beyond computer vision and graphics, problems like astronomy, metrology, etc., problems in simulation. But now with this additional information for the network, you can actually get high quality results. So putting it all together, this provides higher quality results than previous techniques, such as scene representation networks. And you can see from these examples in the synthetic nerve data set that we are able to do very high quality view dependence. Note also that the view dependence of the theta phi parameters are really critical. That enables us to consider these kinds of complex reflections like on the scene, where on the right-hand side, I have fixed the viewpoint, but I let the color vary according to the viewing direction. And you can see that it is actually view dependent in terms of the color. Similarly, here you can see on the right-hand side, I fixed the viewpoint, but the color is varying with the viewing direction. This is very important for capturing these kinds of highlights and glossy effects. Furthermore, although there is no explicit 3D geometry, you can find the expected ray termination depth, and you can get some kind of pseudo geometry from that, which is quite detailed and sufficiently detailed that in augmented reality applications, you can insert an object and have the occlusion relationships be correct. I now want to switch gears a little bit to talk about some of the impact that the neural radiance fields has. The next video I'm going to show is Mark Zuckerberg, the CEO of Meta, talking about the impact of neural radiance fields and their applications in inverse rendering to acquire material properties and how that can be relevant to the metaverse.
Dispensable. Yeah, so one example is being able to build and manipulate.
Again, this has
complex
audio.
3D objects.
Let me know if you can't
This
hear.
is central to the metaverse, but it's hard to build 3D objects from scratch. It's much quicker and easier to just use physical objects as templates.
Today, there's no easy way to do that. So we're researching 2 different technologies to solve that problem. The first one uses machine learning-based neural radiance fields to reconstruct the appearance of a 3D object from multiple 2D images taken at different angles. This method can reproduce even the finest details of an object.
All right, so we're going to scan Teddy, not just because he's super cute, but also because he's got the right dimensions and level of detail for what we're trying to replicate. So here's how it works. So we just scan him on the phone. And that's about it. Right now, this takes some processing time, so we got it ready beforehand so we could check it out. Oh, wow. The level of detail on this is impressive. You can kind of see all these fine elements of it, like each individual strand of its hair. And you can even see through the semi-transparent bow tie that he has on. It's pretty awesome.
Yeah, it's just a beautiful reproduction. The second technology captures geometry and appearance directly.
So here we used a different technique called inverse rendering to scan an object into its digital twin and then bring it into augmented and virtual reality. And it responds dynamically to the lighting in the VR environment. And when you throw it in the air against a wall, or if you bounce it off the ground, it's going to respond the same way that the physical object would. So we used Spark to put the virtual object next to the physical one here. They're almost identical.
Neither approach is real-time yet, and each has its limitations. But the goal is to let you quickly and easily make physical objects a part of your virtual world. Dispensable.
All right. Now, this field is moving very fast. So he ended that video by saying neither approach is real time. And immediately after that, we have this method from Thomas Mueller and colleagues at NVIDIA, which introduces this notion of instant neural graphics primitives or real-time nerves, which was named by Time magazine as one of the best inventions in 2022. The idea is essentially to use a multi-resolution hash encoding, effectively a hybrid method which includes a multi-resolution grid of features, so it's not purely just a continuous MLP as in the original NERV paper. Given any point X, you look up these features from this multi-resolution grid, and it's a hash grid, so that enables collisions, which enable actually greater robustness. And then you concatenate these features and just use a very small MLP to decode them into the density and color. With this, you can see this is real time, how fast the optimization goes. In a few seconds, you can reproduce these NERV models, and thereafter you can render them in real time. Last year, there was an alternative approach proposed by Kerbel et al., which was 3D Gaussian splatted radiance fields. It's actually an intriguing effect that does not include any neural components. There's no neural network, a multi-layer perceptron. You are effectively representing this volumetric appearance with a number of Gaussians that are splatted into the scene. With that, you can, at real-time frame rates, capture these kinds of very impressive scenes. Neither of the last two papers is my own work, just to make it clear, but it shows the ability of these neural radiance fields in view synthesis to really capture these kinds of high-quality visual effects now in real time. Moreover, with the advent of this technology, including software, for instance, neural graphics primitives, for example, it has been widely used in industry to create these kinds of digital twins of real-world scenes. And even lay users have actually used it to create neural radiance fields and these kinds of fly-throughs of environments. Here, presumably, the source images were acquired using a drone, which enables you to create a neural radiance field for a landscape. I'm also involved in an IARPA project, RIVA, that seeks to use NERF and related techniques to, from a few images at varying altitudes, be able to create very immersive visualizations. You can even do this for your dog, and of course, post the results on X or Twitter. And you can even zoom in. Now, one of the things about the NERF algorithm, because it's volumetric, is it just does kind of fill in the space inside. But notice that this is kind of a furry object that, again, you're able to reproduce the visual effects very well for view synthesis and virtual reality types of applications. You can even use NERFs within language models. Again, not my own work. This is from Berkeley, where you can connect a local large language model to it and enable editing of these kinds of NERF representations for 3D. In general, because most local large language models and generative AI are trained on large-scale 2D image data, we need some kind of scaffold to extend them to 3D data, and the neural radiance field representation is essentially that scaffold. Now, the student authors of the NERF paper went on to positions at Google and Luma AI, where they showed that this algorithm could be used in production. So Luma AI has an iPhone app, which I encourage you to check out, that you can take a bunch of images of an object of interest and you can create a NERF of that. Google Street View is using these NERFs to zoom in to, for example, a restaurant. I'll just play the video.
If you're considering a visit, you can virtually soar over the building, find the entrances, and get a sense of what's in the area. With the time slider, you can see what it looks like at different times of day and what the weather will be like, so you know when to visit. To help you avoid crowds, we also point out areas that tend to be busy, so you have all the information you need to confidently make a decision about when and where to go. If you're looking for a bite to eat nearby, you can explore all of the eateries in the neighborhood. You can even glide down to the street level to explore restaurants and peek inside to understand their vibe before you book your reservation. This stunning photorealistic indoor view is powered by Google's Neural Radiance Field, or NERF as we call it. With NERF, we use 2D images to generate a highly accurate 3D representation that models the true complexity of what a place is like. To transform ordinary pictures into stunning 3D models, our artificial intelligence seamlessly predicts where different colors should be applied in space, so you can see if a restaurant has an awesome outdoor patio or a great bar area.
Finally, I'm going to talk about some of my most recent work, which was published at SIGGRAPH this past year, where the goal is to create personalized avatars. This has now received a lot of attention. For example, the Vision Pro from Apple, codec avatars from Avatar, Project Starline, where a number of my former students are key from Google. For the next generation of video conferencing applications. But typically, all of these methods require significant hardware setup with multiple cameras, light stage capture, or depth information. The question is, can you get real-time radiance fields from a single image and, for example, use that for video conferencing? Now, what we were able to show is, at least for portraits, you can do this very well. And in fact, the data you need for that need to be neither captured on a light stage nor even rendered. You can just use existing generative adversarial networks, GAN models that are used to create faces, and for other classes such as cats I'll show later, and use these to provide essentially an unlimited source of training data. What I'm going to show now is images captured just in a cell phone. There's no frame-to-frame coherence. Each individual image is processed separately in real time. And you can capture the images and then turn your viewpoint and show examples where you have a 3D representation of the face. This was, again, done in collaboration with colleagues at NVIDIA. Again, no person-specific training. This is just a generic, generalizable model that works off the box for any face. And it enables accessories to be used as well without any problems. You can change the output view. So you can imagine in a video conferencing example, you change the view and redirect the gaze. You have the output depth as well. You can put on and off glasses. It's not effective. Here are some of these results. Notice also that you can have paint in it, complex hairstyles, babies, and it still works. You can even generalize it to paintings and dolls, which don't quite correspond to realistic face. And even in these cases, from the single image, you have this view-dependent neural radiance field can be captured in a single feed-forward pass. We can also apply it on cats, which is another example, as long as you have a GAN model. Here is an example where you take a monocular RGB video, a standard monocular RGB video, and you want to be able to output novel views. There is some flickering because there is no explicit notion of frame-to-frame coherence. Each of these frames is processed separately in real time, but can be applied to a video. And you can also use it in the avatar context to drive video or drive your avatars. And you can lift your stylized 2D avatars to 3D in real time. I'm going to skip the comparisons. Of course, there's a number of comparisons to recent work, which shows the much higher quality of our results. Okay, you can also use it to lift text-based avatars to 2D, 3D. Nowadays, you can type in text and generate an image, but there is much less training data in 3D. So methods like these provide a bridge to go from text to 3D information, because you can simply run them on the generated images and you can get now these kinds of 3D representations. And finally, we use, there was a demo at the SIGGRAPH 23 Emerging Technologies where the face is actually displayed on a light field display that enables you to actually display it in realistic 3D. And you can use this for 3D video conferencing. There's a lot of potential for the next generation of video conferencing methods. In conclusion, I started with this notion of what is the right scene representation. And we started with a traditional 3D geometry representation disparity. Geometry in computer graphics has long been represented with meshes and depth maps. Neural radiance fields rethink the notion of 3D geometry with this kind of soft volumetric model. Since 3D and 3D geometry is a core component of methods in a wide range of fields, including all the traditional simulation fields and engineering, many applications well beyond computer graphics and vision can benefit from these techniques. Also, many of these methods leverage past work and often rediscover past work. Volumetric representations in computer graphics have a long history of 30+ years. That's what we are leveraging. And we, in fact, cite some of the papers from the 90s and earlier. There has also been a lot of work in point-based renderings using points as a display primitive. Again, has an almost 40-year history in computer graphics. And effectively, the Gaussian splatting algorithm is repurposing that history of point-based methods for improved radiance fields. Furthermore, the representations, such as the multi-resolution hash grid in Instant NGP, effectively represent these feature fields. And we can leverage an older history of light transport representations for feature fields, including potentially clustered principal component analysis, clustered tensor approximation, and there have been methods for tensorial radiance fields. But there has, in recent years, also been a zoo of new representations proposed, such as triplanes, multi-resolution hash grids. And one of the interesting things is to bring that back to traditional computer graphics. We have an initial paper on applying them to pre-computed relighting. More broadly, can we rethink the representation of images themselves? Images have always been represented with a discrete grid of pixels. Is there a better representation that can overthrow that traditional approach? In a paper that we presented at SIGGRAPH Asia this year, we developed a neural network that can take account of explicit discontinuities in a feature field, curved and straight line discontinuities, and otherwise be continuous, allowing infinite discontinuity preserving zooms. And of course, there are important acquisition generalizations. Dynamic scenes, I think, is very important. Inverse rendering to recover lighting and material properties, enable you to do relighting, light transport acquisition. And we are seeing a lot of very exciting work in all of these different domains. Finally, I would like to acknowledge my students and collaborators. What I presented has been a long-term research challenge for much of the past decade and beyond. And of course, the collaborators, Pratul, Ben, Matt, Tanchik on the neural radiance fields, and newer work by Alex Trevethick and Kyle Lin. And many of my collaborators, including, of course, Renning and John Barron on neural radiance fields, and the funding agencies that made all of this research and provided the funding to make it possible. Thank you again for inviting me, and I'm now happy to take questions.
Great. So thank you for a wonderful talk. So I think for the Q&A segment, people who are on Zoom can enter their questions into the chat and I'll read them off. And anyone here in the room can also ask questions. I guess I'll just take questions, as they come in. So I guess I'll start by asking a question of my own. Do you know of any methods that that deal with quantifying uncertainty For this task, like if you had, say some missing information because you didn't have like enough views,
Mhm.
do you know of any methods that could sort of give like
So
range of possible?
so in the traditional 3D scanning literature, this is something that certainly people have looked at, predicting the next best view to fill in information. I think there is relatively less work in neural radiance fields per se in that literature of quantifying where the uncertainty is and predicting next best view, but it is definitely an interesting problem where we can probably leverage some of the older work in the 3D scanning literature in this area.
Great. And I guess one other question, a more general one. What are some directions that you wish more people would look into moving forward with radiance fields?
So I think there still remains a lot of interesting work on the core representations. But beyond that, I wanted to point out some of the last two bullets here. So one is that there is a potential to change the representations used for traditional images, or in fact, the neural network and the learning paradigm used for traditional images, which has been a sort of 2D grid. So in a sense, neural radiance fields changes the representation of 3D geometry from being either a geometric mesh or a 3D volumetric grid to a continuous representation. There is a lot of potential to do that in other domains, in particular for images themselves or light fields or higher dimensional quantities. Beyond that, there are a number of acquisition scenarios. So inverse rendering and acquiring lighting and material properties remains a very important and active topic. And considering dynamic scenes, I think, is a very critical topic because, I mean, there's a lot you can do on static scenes, but of course, dynamic scenes in video is much more challenging area. So those are some of the key challenges that I see. And there continue to be important problems just in terms of the core representation of how do you compress and efficiently represent the volume, and how can you use that more effectively for faster training and faster inference.
Great. So I guess I'll give people in the room a chance to ask questions.
I have a question. First of all, am I audible?
Yes.
You hear?
All right. So it's about one of your slides early on in the nerve part of the presentation. So you mentioned that lighting is captured in the nerve, and
Yes.
so I kind of didn't follow. Maybe you did mention it.
Well, all right. So in effect, you have an emissive volume. So the effects of the lighting are not decoupled. So the view synthesis will always happen with the lighting that was in the scene when it was captured.
Right. My question is how you import these into a differently lit scene.
Yes. So in the traditional nerve where you're just doing view synthesis, you don't have the capability for relighting. And that's why I said these kinds of inverse rendering applications, which enable you to acquire the material properties, are important because they would enable you then to use these models in traditional computer graphics where you can change both the lighting and the viewpoint. Now, one of the first works we did on this, which was originally deep reflectance volumes and subsequently using neural radiance fields, is that instead of the volume storing color and the density, you store also like a BRDF function that effectively says how it reflects light. And if you do that, you have basically these volumetric reflectance fields, and there has been subsequent work on that would then enable you to do relighting. However, there remain challenges because the problem just from taking a number of viewpoints is fundamentally ill-posed. So the correct way of having representations that enable you to correctly infer material properties for relighting in specular scenes remains an ongoing challenge. I mean, we have some work coming out at CVPR this year, but it definitely remains an important challenge.
Thank you.
But in the traditional neural radiance field method for view synthesis, you're just trying to do view synthesis. The lighting is baked in.
Great. Does anyone else have any questions? Oh, okay. I see. Oh, okay, there's a Q&A. Great. So Arijit's question. Have you given any thought towards disentangling the NERF representations for objects in a scene, like forming NERF models?
Yes, and there have been some works on doing that. So I mean, at a core level, I mean, this is just a segmentation problem, right? So if you have like a NERF of the entire scene, you can extract the volume of individual objects as long as you can segment them out in 3D. But there have certainly been works that try to simultaneously obtain the information from the different objects. And then compositing can be done because, I mean, again, it's just you're compositing the volumetric representation. So you can composite and recombine. And one of the early papers, which was Giraffe in CVPR 21, Best Paper Award, did kind of take a step in that direction as well. So it's certainly something people have been looking at.
Great. Yes, does anyone else have questions? Great. I guess just one more that I have. Where do you see the limit of NERF in terms of or NERF-based methods in terms of reflections? So like if I have, you know, a reflection of a reflection of a reflection, I guess how far is the limit and how do we push it further?
Yeah, so I mean, in terms of specular scenes and global illumination, multiple bounces, I mean, we do have a representation that is coming out in CVPR this year. Of course, I mean, if you really have a scene that has kind of this ray tracing of multiple reflections, that is more challenging to handle. But at some level, it's not necessarily a fundamental limitation of the NERF method. It's just that you need to be able to trace these rays through and consider global illumination. And the problem is like a volumetric representation is a little bit kind of challenging for that because you want reflection on a hard surface, right? So you may need to augment the representation to enable like clean reflections. But yeah, I mean, these are all very good comments about some of the challenges in the current state of the art of view synthesis and relighting, where we are looking at them and have made some progress. But going back to your initial question, I do want people to work more on all of these different problems so that we have robust solutions to them.
Great. So thanks everyone for coming, and thank you, Ravi, for a wonderful talk. Yes, if anyone, if anyone has any further follow-up questions, I mean, I think Ravi's contact, I think his email is on the announcement. So let's all give Ravi a hand. Hey.
All right. So thank you very much for coming. And yeah, thank you.
Thank you.